Alright, this video is going to give you an overview of the first unit for grade 9 advanced science in preparation for your test, or if you're preparing for a retest. You have at the back of your science booklets a checklist for each unit. You should have used this to study if you're doing a retest, and if you're just preparing for the test, you should have this in front of you as well. So there's some basic vocabulary that you should be familiar with. That is not an exhaustive list. There are other things, but you can see, for example, are you familiar with the different pieces of equipment that we used in the lab during this unit? Those are not the only things we used, but be sure you know and can identify different lab equipment. The meniscus, when you're using a graduated cylinder, the curved surface of the liquid in the graduated cylinder is the meniscus. Things like an endothermic reaction, an exothermic reaction, you should be able to describe what those mean. Different terms, any new vocabulary we learned. Solving basic volume problems, there was a whole worksheet on that. There are some formulas for volume that you need to know. A rectangular prism, like a box, its formula for volume would be volume is length times width times height. A cylinder would have a formula where the volume is the area of the base times the height, but the area of the base of a cylinder is a circle's area, so pi r squared times h. A cone would be very similar to a cylinder, but a cone comes to a point. So for shapes that come to a point, you take the same formula, pi r squared times h, and you divide by 3. The pyramid would be like the rectangular prism, but again, it comes to a point, so therefore we divide by 3 again. L, length times width times height, divide by 3. And finally, the sphere, this formula is a little bit different. It's not just area of base times height. This one is 4/3 pi times the radius cubed. Now, a good way to study those things would be to get some flashcards made up, put the name of the object on one side, maybe say volume of cylinder, and on the other side write its formula. Make sure you know the formulas. If you're not going to do that kind of studying for formulas or the vocabulary up above, then it's going to be a hard thing to do on this test. So some good strategies like flashcards, the best students do those sorts of things. So if you're not willing to put in that work, you're not going to see an improvement in the course. Be sure you know how to read the volume of a graduated cylinder. I'm not going to show that in this video, but you know that you have to look at eye level, you have to be able to describe the major and the minor scales and use them looking at the bottom of the meniscus in the cylinder to read the volume. If you need practice on that, if you didn't do so well when we did the lab on this, then you can ask for some extra help, come in and actually practice on some cylinders. That's easy to review. From middle school, you should know how to find volume of a solid by water displacement. If you put water in a graduated cylinder, let's say 20 milliliters, and you drop in an object and it sinks, if the volume goes up to 27 milliliters, then the volume of that object must have been 7 milliliters. It went from 20 up to 27, so the difference, 7 milliliters, would be the volume of the object that sank in the water. So that's a very basic idea. We used it in the experiment for percentage of air in sand. We're going to review in a moment how to do calculations for percentage of air in dry sand, in marbles or pebbles, any kind of granular solid where there's air in between the particles. That is the major calculation, by the way, in this unit. So of all the labs we did, that one had unique calculations. So be sure that you are able to do those calculations with confidence. Calculating a percent change in mass or a change in mass before you can find percent change, that's a very simple calculation. You did it several times in the experiments on law of conservation of mass. Be able to convert between scientific notation and the normal expanded or decimal notation back and forth. There's lots of review on that online on YouTube if you're having trouble with it. Know how to use your calculator to enter scientific notation as well. Significant digits are a really important idea both in this unit and throughout the course. We're going to use them all the time. Be able to count the number of significant digits in a measurement, know how to round off when you're adding measured numbers together in your answer, know adding or subtracting, know how to also round off the answer when you're multiplying and dividing. There are different rules for adding, subtracting than there are for multiplying and dividing. Know how to use unit multipliers to convert simple units, like if you want to convert inches into feet or feet into centimeters, things like that. We use unit multipliers to do those conversions. Know the different parts of a lab report. Be able to describe the different parts that are included in the title page. Know what goes in an abstract. Know what good data tables would look like. In this first unit, we didn't really make any graphs, so you don't have to worry about graphs, but understand what the conclusion should involve as well in a lab report. Some basic statistics. If you're given a set of numbers, be able to find the mean, what most people call the average, the median, the mode, and also the range. There's a YouTube video that we made for those things. If you searched on YouTube, you can find dozens and dozens of videos that will explain how to do those things as well. The really big idea in the first unit is the law of conservation of mass. During physical or chemical changes, the mass will not change as long as you don't add anything or allow something to escape. Notice how there's 3 parts to that definition. The first part, during chemical and physical changes. The second part, mass will not change. And the third part, as long as you don't add or lose anything from the container. That was right out of our notes, and it's the big idea in the first unit. A physical versus a chemical change. Physical changes are things like phase changes, so melting and boiling and freezing, evaporation, or things like taking a piece of paper and cutting it into small pieces. Physical changes, there are no new products, there are no new substances produced. If you started with water frozen, you still have water after it melts. So there's no new substances produced. In a chemical change, you do produce new substances. So when we added Alka-Seltzer to water, we produced a new substance. We produced carbon dioxide gas, right? So be sure you understand the difference. Chemical changes, we had 4 or 5 different evidences of change. I won't go over them here. They're right out of your notes. I just mentioned the gas in Alka-Seltzer and water, carbon dioxide or CO2. In each of the experiments that we did on the law of conservation of mass, there were unique errors in them. You need to know what those errors were for each experiment and whether they would cause an increase or a decrease in mass. For example, in the Alka-Seltzer and water experiment, when you added the Alka-Seltzer to water, it produced CO2 gas, which escaped from the bottle before you could put the lid on perfectly. So some gas would always escape from the bottle, which would make the mass decrease because gas was escaping. In that same experiment, if you didn't put the lid on tightly, gas would continue to escape during the experiment, and that would also make the mass decrease. So for each of the 5 experiments, dissolving salt, melting the ice and turning it into water, the Alka-Seltzer in water, mixing 2 solutions to form a precipitate, and also the heating of the copper with sulfur, in each of those 5 experiments there was a unique error. You did an online safety course on WHMIS. Make sure you know what WHMIS means. GHS, the Global Harmonized System, Safety Data Sheets, SDS. You should be able to recognize and interpret the different pictograms, the safety pictograms that might show up on a label for a chemical. Know what the various safety precautions are for various hazards, For example, if something were corrosive, you should wear gloves and safety goggles, right? Something's flammable, you should keep it away from sparks, things like that. You should also be able to understand the different major sections of the SDS. You wouldn't have to memorize them all, but if you were told a given section, for example, the chemical and physical properties section or the first aid measures section, you should know what that section of the safety data sheet is for. So this was all in the checklist. You should be using it to prepare for the test. If you wrote the test and now you're doing a retest, you didn't do so well, did you pay attention to this list when you prepared? All right, so now I want you to have some loose leaf. And to do this well, you need to be involved. If you're going to sit and just watch the video from this point on, you're not going to get what you need to from this review. All right, so you have to pause the video, try the questions yourself when you're able, and check your answers as we go along. All right, so the first question, how many significant digits are in each of these measurements? Quick review, every digit that is not 0, so the 2's in this first measurement, those are significant. Zeros are the digits that are confusing. When you see a decimal like we see here, zeros that are at the end of the measurement are always going to be significant. So if you see a decimal and there's zeros at the end of the measurement, they will count. So this has 3 significant digits. When you see zeros at the beginning of a measurement, they don't count. Leading zeros are never considered significant. So how many digits in the next measurement would be significant? Well, the first 3 digits are zeros. They're starting off. They don't count. So only the 5. This has 1 significant digit. What about part C? How many significant digits do you see there? Well, we set up above, if you see zeros at the end of the measurement and you see a decimal, then those zeros count. If you see zeros at the end of the measurement, like we have here, but there is no there's no decimal showing, then those zeros do not count. So therefore, this has only 1 significant digit. In the next one, how many significant digits do you see there? The 2 zeros at the beginning are not significant. Leading zeros are never significant. The 2 is definitely significant. I see a decimal place. The decimal is showing, so the zeros at the end will count as significant digits. That has 3 significant digits. 5050, the zeros at the beginning do not count. The 5's count. The 0 at the end, because we see a decimal place, it is significant. And if you recall from the worksheets we did on this, zeros that are in between non-zero digits, like this 0 in between the 2 5's, it will count. So only the first 3 zeros there do not count. This has 4 significant digits. All right, so if you know you don't understand this, you have something very specific to ask for help on. Or do a search on YouTube counting significant digits, and you'll find explanations there. Question 2, find the area and the perimeter of this rectangle. Now this is not a question about finding perimeter and area. This is grade 9 advanced science. That's not the point of the question. The point is, can you use the rules for significant digits? When you want to find the perimeter, you know you're going to add 2 times the length plus 2 times the width. The length will be added twice and the width will be added twice. So we're adding these measurements together. The rule for adding measured numbers or subtracting measured numbers is that you round off the answer based on the fewest number of decimal places. So what we're going to do to find the perimeter is 25 plus 25 plus 8.27 plus 8.27. Pause the video, grab your calculator, and get a number for that. So 50 plus 8.27 and another 8.27 your calculator should say 66.54. Here's a simple test. Did you pause the video, get your calculator, and do that, or did you just watch? If you're just watching, you might as well stop the video because you're not going to review the way you should. Now, the rule for adding or subtracting is to round off the answer based on the fewest number of decimal places that were in the measurement. So when we look at the numbers that were being added together, the 8.27s both had 2 decimal places, while the 25s, they have no decimal places. Since these guys have no decimal places, these guys have 2 decimal places, we need to round off the answer so it has no decimal places. Round it off so it has the fewest number of decimal places. So with my calculator giving me 66.54, we're going to have to call that, what will it be, 66 or will it be 67? Well, you look at the next digit after the decimal and it was a 5. So if it's a 5, 6, 7, 8, or 9, we round up and we call it 67 feet. There's the perimeter of that rectangle. Now find the area. The area, as you know, is the length times the width. And again, that's not the point of the question. When you multiply measured numbers together or you divide, there's a different rule for rounding off the answer. So go ahead first and calculate the area. Grab your calculator and multiply those two numbers together and write down what your calculator says. So that's the number on my calculator. Feet times feet, it'll be feet squared as an area. But how do I round off that answer? The answer now is to look at not decimal places, but significant digits. The first number, 25, has 2 significant digits, just like we were doing up above, counting significant digits. The 8.27 has 3 significant digits. So we have to round this number off to the fewest number of significant digits. We're going to round it off so it has just 2 significant digits. If I call it 207, rounding up the 206 to 207, it's going to have 3 significant digits, right? Based on the counting rules we did earlier. So that's not good. How do I make it have just 2 digits? Well, we're going to have to round it up even further. We can call it 210, and we don't put a decimal at the end. That 0 will not count, and that will now have 2 significant digits, the 2 and the 1. Or you could put that in scientific notation, something we're going to practice next. Call it 2.1 times 100, but 100 is 10 squared. There is scientific notation version of the same answer, and again it has 2 significant digits, 2.1. Either one of those answers would be fine. So if you understand that you struggle with finding or rounding off answers when you add, subtract, or multiply, divide, you have something very specific to ask for help on. Can you convert numbers to scientific notation? Well, here's 4 examples. Scientific notation, as you saw up above in that number we just did, it has to have a number at the beginning between 1 and 10. And then it's multiplied by a power of 10. That's scientific notation. So this number 25,000, we're going to first of all just realize that it has a decimal at the end. It's not visible, but there's a decimal at the end of that number. And if we move the decimal 1, 2, 3, 4 places, we're going to get a number between 1 and 10. We'll get 2.5. So we were told to keep 2 digits in the answer, so we can write 2.5. Because I moved the decimal 4 places, we can say times 10 to the 4. And finally, because the number 25,000 is a large number, it's bigger than 1, the exponent stays as a positive 4. If we had had a small number, like in the next question, part B, we would say negative 4. Okay? When the power of 10 is positive, 10 to the positive 4, the number is a big number. If the power of 10 has a negative exponent, 10 to the negative 4, then the number is a small number, less than 1. So for part B, I can tell right away it's a number less than 1. It will have a negative exponent when I write it in scientific notation. The decimal is over here on the left. How many places do you move the decimal to get a number between 1 and 10? Well, we have to move it 1, 2, 3 places. We'll now have 1.57. And then because we moved it 3 places, 10 to the 3, and because it's less than 1, the original number, negative 3. 1.57 times 10 to the negative 3. But we were told to round it off so it has only 1 digit. 1.57 has 3 digits. To have only 1 digit, we are going to keep the digit before the decimal. So now we look at the next digit. It's a 5, so we have to round that up. It's going to become 2 times 10 to the negative 3. There's the scientific notation version of that number, rounded off with 1 digit. Try the next two on your own, so pause the video and give those a try. This next one is again a number less than 1, so when you write it, you should have a negative exponent on the 10. To get a number between 1 and 10, we have to move the decimal 1, 2, 3, 4, 5 places, and I get 3.47 times 10 to the negative 5. 5 because I moved the decimal 5 spaces, negative 5 because it's less than 1. Well, we needed only 2 digits in the answer, so let's round it off. Instead of 3.47, which has 3 digits, we'll call it 3.5 times 10 to the negative 5. The next one, 457.2, is bigger than 1, so the exponent on the 10 will be a positive exponent. To get the number between 1 and 10, we move the decimal 2 places. We'll get 4.572 times 10 to the positive 2. But we needed to keep only 3 digits in the answer, so we'll call it 4.57 times 10 to the 2. The 7 does not get rounded up because the next digit was 2, which is less than 5, so we just keep it as 4.57 times 10 to the 2. So there you have scientific notation. Some of you, if you're doing a retest, you may have had no clue on your original test how to do this. If you realize you still struggle, you have something very specific to ask for help on. I don't understand scientific notation. So ask for help in a very specific way. Finding volume was a big part of this first unit. We did a large worksheet on this. You're supposed to know the different formulas for volume. They will not be given to you on the test. You have to memorize those. So here we have a cylinder. We want the volume of the cylinder. So volume of a cylinder is the area of its base, which is a circle, pi r squared, times its height. The r is the radius, and in the question we're told the radius. Notice that it says it's in inches, 2.20 inches. The height is 12.00 inches. If we're going to go find the volume, it will be in cubic inches. But we need to convert it at the end to cubic centimeters. So let's jump in first and get the volume in cubic inches. So pi is 3.14. This is how your answer should be laid out. You've written the formula first, and now you're putting the numbers in. The radius is 2.20 inches squared times the height, 12.00, don't leave out those zeros, inches. You grab your calculator, 3.14 times, if you have a squared button, you can say 2.2 and then press the squared button, or you can just times 2.2 by itself twice when you're on the calculator, and then multiply by the 12 at the end. My calculator gives me this big number. I hope you're doing this yourself, not just watching. Pause the video if I'm going too fast for you. 182.3712 is what my calculator says. But we're multiplying these measured numbers together. This is significant digits. We talked about this a few minutes ago. So you look at the measured numbers. The radius had 3 significant digits, 2.20. The height has 4 significant digits, 12.00. So I'm going to round off my answer to have the smaller number of digits, 3 digits. So I'm going to just call this 182 cubic inches. Now we need to convert this to cubic centimeters. So here comes that from our checklist, converting units with unit multipliers. 182 cubic inches. You need to know some recipes. You need to know how many centimeters are in an inch, how many inches are in a foot, how many, what else? How many milliliters are in a liter, how many grams are in a kilogram. Those are basic recipes that every grade 9 student should know. So I'm going to try to convert cubic inches into cubic centimeters. So I'll put inches in the denominator of this unit multiplier, and I'll put centimeters in the numerator because I'm trying to find cubic centimeters. Now, because we had cubic inches, we're going to need to use this conversion, this unit multiplier, not once, but 3 times. We'll need to put inches 3 times on the bottom and centimeters 3 times on the top. That way we'll have inches times inches times inches, which is cubic inches, and that will now cancel with the cubic inches that we had out front. And we'll have centimeter times centimeter times centimeter. My answer will be cubic centimeters. Now the recipe for inches and centimeters, say it to yourself. There are 2.54 centimeters in 1 inch. So I'm going to put 2.54 beside centimeters, and I'm going to put 1 beside inches. I'm going to do that 3 times. 2.54 centimeters in 1 inch. 2.54 centimeters in 1 inch. Grab your calculator and get the answer to that. 182 times 2.54 3 times will give you 2982.445648 is what your calculator says. But we're going to round it off because the original volume had only 3 significant digits. We're going to round that off to have only 3 significant digits. So we can call it 2980 without a decimal. The 0 at the end will not be significant. So that has 3 significant digits. Or in scientific notation, 2.98 times 10 to the positive 3, right? You have to move the decimal 3 places to get 2.98. It's a big number, so positive 3 cubic centimeters. Make sure you have units with your final answer. Number 5, pause the video and see if you can do that yourself. So this time we have a sphere. We're told the diameter, not the radius, but we know that the radius is half the diameter. It's dropped into a cylinder with some water. This sounds to me like water displacement. What will be the final level of the water when this sphere sinks? So the formula for volume of a sphere, you're supposed to know the formula, is 4/3 pi times its radius cubed. We don't know the radius, we know the diameter. So let's calculate the radius. It's half of the diameter. So we take 5.6 and we divide by 2. That's going to give us 2.8 centimeters. Now we can put this into the formula and we can calculate the volume of the sphere. 4/3 times pi times the radius, 2.8 centimeters cubed. Cubed means timesing it by itself 3 times. So we go on our calculators, 4 times 3.14 times 2.8. If you have a cubed button or you know how to raise to the power of 3 on your calculator, do that, or multiply it by 2.8 2 more times. And then don't forget to also divide by the 3, and you should get 91.9057, etc. on the calculator. Because we cubed the centimeters, the units are cubic centimeters. Now, how many digits should we keep? 2.8 has only 2 significant digits. This is multiplication, so we should round it off to 2 significant digits. We're going to call it 92 cubic centimeters. Now, this sank in the water. There was already 46.1 milliliters of water, so therefore the volume will go up by 92. Remember that 1 cubic centimeter is the same as 1 milliliter. So this is the same as saying 92 milliliters. So the final level of the water would be the original level, 46.1 milliliters, plus the 92 milliliters, the volume of this sphere. Notice we're now adding measurements. What's the rule for adding or subtracting with measured numbers? You round off your answer based on decimal places. So because the first number has 1 decimal place, 46.1, but the next number has no decimal places, we're going to round this off to have no decimal places. So 92 plus 46.1 gives me 138.1 milliliters, which we will round off to just 138 milliliters, no decimal places in the final answer. All right? I hope you got that. Okay, we're almost done. Calculating change and percent change in an experiment. Finding the change in mass is not as simple as it sounds. You don't just take the two numbers and subtract them. Finding a change in mass, this could be on another flashcard for things that you're studying. Put finding change in mass on one side of your flashcard. On the other side, you would write the final mass minus the starting mass. So what we need to do here is the starting mass before we added the Alka-Seltzer to the water was 22.15 grams. The final mass was 21.98 grams. So the change in mass is the final mass minus the starting mass. So we'll take the change in mass is 21.98 grams minus 22.15 grams. Notice why we subtract in that order. The mass went down. It was 22 and now it's under 22. It dropped in mass. So because it dropped, the change in mass is going to be a negative answer. If the mass had gone up, the change in mass would be a positive answer when we subtract like this. So 21.98 subtract 22.15. Subtracting, we're going to keep 2 decimal places in the answer, and we get negative 0.17 grams. That's the change in mass. Now find your percent change in mass. The percent change in mass is the change that we just calculated divided by the starting number, starting mass, and multiply by 100. You have to multiply by 100 to get it to be a percent. So we'll take the change, negative 0.17 grams. We'll divide by the starting mass, which was 22.15 grams, and we'll times by 100. Grab your calculator and get the answer. When you're dividing like that, you base your answer on significant digits. 2 digits in the numerator, 4 digits in the denominator. We're going to keep 2 digits in the answer. Because it was a negative number on top and a positive number on the bottom, our answer is negative. So we get negative 0.77% change. A little bit less than 1%. Now some other students did the experiment and they got these changes. Let's add the change that we got, which was negative 0.17. So this is the change that we had up above. Calculate the mean, the median, and the range for the results, including our result. If you think you know what you're doing, go ahead and do this, but be sure to show your work. The mean is what we normally think of as the average. So you just take all the numbers, 0.05 plus, don't forget the negative sign, negative 0.09 plus negative 0.11 plus 0.00. Now I'm just going to do this plus ... I'm adding all my numbers together, and then you divide by how many numbers we added together. So there was 1, 2, 3, 4, 5, 6, 7 numbers in all, so we divide by 7. So let's do that on your calculator. Don't forget the negative symbols. 0.05 plus negative 0.09 plus negative 0.11 plus 0 plus another 0 plus 0.02 positive plus negative 0.17 equals. My calculator says negative 0.3. But we were adding all those numbers together, so we know we should round off the answer based on decimal places. So we're going to call it 0.30, so it has 2 decimal places. We divide that by the total number of numbers, which was 7. Divide by 7, and keeping 2 significant digits. The 7 is not a measured number, it's a counting number, so we don't look at that for rounding off. And we'll say negative 0.043, when I round that off, grams is my average change in mass. So there was the mean. Now let's do the median. The median is the middle number. So we take the measurements and we're going to put them in order from smallest to biggest. So negative 0.17 was the smallest, negative 0.11, negative 0.09. Those are all the negatives. Then we have 0, we have another 0, and then we have a 0.02 positive, and we have a 0.05 positive. So there's 7 numbers in all. The middle one would be the 4th number in. So this number here is the middle number, so that is the median. The 0.00 grams is the median. The range. The range is a measure of how spread out the numbers are. To find the range, we just take the largest number and we subtract the smallest number. So our largest number was 0.05 grams. We subtract the smallest number, which was negative 0.17 grams. Grab your calculator, 0.05, take away negative 0.17 gives me positive 0.22 grams. So there was 0.22 grams between the smallest and biggest number in those measurements, or in those calculations. That leads us to the big calculation for the lab, which was percent air in sand. Recall what we did in this experiment. You took some dry sand, you poured it into a graduated cylinder, and we found in this case that its volume is 35.1 milliliters. Then we poured some water in a graduated cylinder, and we found its volume, just the water, is 22.5 milliliters. We then added the sand to the water. And when you add the sand to the water level goes up, and it went up to 49.2 milliliters. Calculate these three things. What's the volume of the sand grains by themselves? What's the volume of the air by itself? Remembering that the dry sand is made of sand grains and air. And then what's the volume of the percentage of air in the sand? There's more than one way to do this. Let me show you a way that I think is a little bit easier. If there was no air, write that down in your answer. Suppose you added 35.1 milliliters of an object, like we talked earlier about a marble, and you added it to 22.5 milliliters of water. If there's no air present in the object, if it's a solid marble or a solid sphere, then most middle school students would say that the total volume will just be those two numbers added together. The object sinks, the water level gets pushed up, you just add those numbers together. So let's say that if there was no air, 35.1 milliliters, the volume of the sand, plus 22.5 milliliters, the volume of the water, this is what the total volume should have been. It should have been 57.6 milliliters total volume. Was that the total volume? Was it 57.6? Well, look back up above. Instead of 57.6, the total volume was only 49.2. Why was the total volume less than what we just expected? It's less because there was air, right? This answer was if there was no air. The 49.2 is less than this because there was air. So how much air was there? So let's calculate the volume of air that was actually in the sand. What we'll do is we'll take what the volume should have been, 57.6 milliliters, and subtract the actual volume. The total volume was only 49.2. The difference between the expected and the actual volume, that difference is because of the air. So if we take our calculator and subtract 57.6 minus 49.2, we get that there was 8.4 milliliters of air. Notice that we're following the rules for significant digits. We're rounding off to one decimal place because we're adding and subtracting numbers. So we now know the volume of the air was 8.4 milliliters. We can go back here and say that. Then how much sand grain was there? Well, if the dry sand, which was made up of sand grains and air, if the dry sand was 35.1 milliliters, and we now know that there was 8.4 milliliters of air in that dry sand, then how much of the dry sand was not air? How much of the dry sand was sand grains? Can you see what we're going to do? So the sand grains, you would take the dry sand volume, which was 35.1 milliliters, and subtract the air. So this was the dry sand. And we subtract the 8.4 milliliters of air. And that's going to give us the volume of the sand grains by themselves. We get 26.7 milliliters sand grains. Just to see if that makes sense, what was causing the water level to rise? When we poured the sand into the water, what was causing the water level to rise? Well, it was the sand grains that was displacing the water. So if you took the volume of the water, 22.5 milliliters, and add the volume of the sand grains that we just calculated, you should get the volume of the sand and water, which is 49.2. Finally, we want to know the percentage of air in the dry sand. Since we want percentage of air, we'll take the volume of air as our starting point, 8.4 milliliters, in the dry sand. So we'll divide that by the volume of the dry sand, which was 35.1 milliliters. And to get a percent, you times by 100. So 8.4 divided by 35.1 and times by 100. And I hope you are thinking about significant digits. We're dividing, so we don't look at decimal places, we look at digits. We're going to keep 2 digits in the answer because the numerator has 2 digits, and we'll call this 24%. The calculator says 23.9, so 24% air. All right, so I hope that helps. There are other videos that we posted on Google Classroom that review the air and sand experiment. Watch those videos, but don't just watch. Pause the video and try it yourself. If you still don't understand it, that's something very specific to ask for help on. Can you explain again the air and sand calculations is what you would ask your teacher. Finally, the last question in this review. Describe the 4 parts of an abstract. The abstract, if you've written your lab report and you saw the video on the parts of the abstract, this is the introductory paragraph in a lab report. So when the first paragraph we read is this, it has 4 basic parts. You're supposed to tell us at the beginning some background. So you might say at the beginning, everybody knows that when you walk on the beach, the sand under your feet is not a pure solid. The sand is made of particles with air spaces in between. That's background information. Then you would tell me the purpose of the experiment. The purpose of our experiment was to calculate the percentage of air in the sand. There you go. Then you would describe the procedure, sometimes called the method. And don't go into any detail here. Here's what I would say in this experiment. To do this, we measured the volume of a sample of dry sand using a graduated cylinder. We then measured a sample of water's volume. We added the dry sand to the water and measured the combined volume. Done. There's the procedure. And finally, you tell me the result. You don't tell me all the individual results like the volume of the sand grains. The purpose of the experiment was to find the percentage of air in sand. So you would simply say at the end, we found the percentage of air in the sand to be 24%. If there was a class average, you might also say that. The class average was 26%. If there was a true value, you might even compare it at that point, right? But that's the basic idea. Some background information, the purpose, why you did the experiment, the procedure summarized, and finally tell us what you found. If you said the purpose was to get the melting point of the naphthalene, then your conclusion at the end of your abstract, you should say the melting point of the naphthalene was 80.5 degrees Celsius. Those are the 4 parts to an abstract. All right, so I hope that helps. Hope you feel you understand the first unit a little bit better. If there are still some specific things in this review or things that were on the checklist you don't understand, contact your teacher with those very specific things for extra help on, or go to YouTube. Better yet, look on Google Classroom for some of those videos that were posted there. You might find something that reviews what you're struggling with as you're preparing for your test or preparing for